In this video, we're going to talk about the probability of a union, an intersection, and a complement of an event, and then we're going to finish with a discussion of odds. So events we know represent subsets of the sample space for a particular experiment. So an experiment we can think of as a particular action being performed. The sample space is all the different possible outcomes for that action, and then events are specific outcomes within the sample space. So we're going to let A and B be two events in our sample space. The union of events A and B is defined as all the elements in the sample space such that that particular event or outcome is an element of our first event or it's an element of our second event. So think of the union as two events as all the outcomes representative of one or the other or potentially both events occurring at the same time. Now the intersection of our two events is going to be all the elements in the sample space such that we have an event that's in event, or we have a particular outcome that's in event A, and that outcome is also in event B. So in other words, it has to be in both at the same time. So what we know about a union from our discussion of set theory is things that are in the union have to be in one set or the other, or possibly both. Things in the intersection have to be in both sets at the same time. So now we're talking about outcomes from an experiment, either outcomes that are in one event or the other, possibly both, or outcomes that have to be in both events at the same time. Now, in order to define some of the key things we need, particularly with respect to our probability formulas, we need to define this term mutually exclusive. So two events are said to be mutually exclusive if they cannot occur at the same time. In other words, if event A is occurring, then event B cannot be occurring. In other words, there's no outcomes that represent occurrence of both events. So what we would say in set notation, if A and B are mutually exclusive, is that A intersected with B is equal to the empty set. In other words, there are no outcomes in the sample space that are in both A and B at the same time. If A happens, then B doesn't happen. If B happens, then A doesn't happen. Now, in terms of probability, we would say that the probability of A and B would be 0 in this case. So the probability of both occurring at the same time is 0. Now, if A and B are mutually exclusive, then the probability of A or B occurring is just going to be the probability of the first event plus the probability of the second event. Think of this in a sense as combining all the different outcomes representative of one event or the other, which also just results in combining the resulting probabilities. Now, if instead A and B are not mutually exclusive, what that means is that A can occur, B can occur, but there are also outcomes representative of both events at the same time. That would be what we mean by saying that something is not mutually exclusive. If our events are not mutually exclusive, then the probability of A or B occurring is also going to be the sum of the original probabilities, but we have to subtract the probability of the intersection. Why is this? Well, this particular probability is representative of all the outcomes that are in both A and B at the same time. Think about those particular outcomes. They're in A and B at the same time, which means they were counted as part of this probability because they're in A, but they were also counted as part of this probability because they were in B. So the particular outcomes for which we've calculated probability here were calculated twice. Because they were included twice in the two separate events, that means we've double counted those outcomes, and it means that just adding the individual probabilities results in a value that's going to be a little bit too high. So we subtract the probability of the intersection in order to keep from double counting, just like we did when we talked about counting the union of two sets. So consider the sample space of equally likely events for rolling a single fair die. So the sample space would just be all the different rolls, which would be the rolls from 1 to 6. The first question, what is the probability of rolling a number that is odd and exactly divisible by 3? So odd and divisible by 3 at the same time. So we can define these two events. So the first event is rolling something that's odd, and the second event is rolling something that's divisible by 3. Well, what different outcomes represent rolling something that's odd and rolling something that's divisible by 3? Well, if it's odd, then it could be a 1, a 3, or a 5. If it's divisible by 3, then that means a number that 3 divides into evenly. It could be 3 or it could be 6. What we're looking for is the intersection of those two events. In other words, specific outcomes in the sample space that represent the occurrence of both events at the same time. Now, the only particular outcome representative of both events is going to be the outcome of rolling a 3. So there's only one way to roll a number that is both odd and divisible by 3 at the same time. So the probability is going to be 1 for that one outcome, divided by the total number of outcomes in the sample space, which is 6. So our probability is going to be 1 out of 6, or approximately 0.167. Now let's change the wording a little bit. So what's the probability of rolling a number that is odd or exactly divisible by 3? So we have the same events defined, but now it's not the probability of one and the other occurring at the same time. It's the probability that one or the other occurs. In other words, if an outcome falls under the first event, then it's included as part of our probability. If the outcome falls under the second event, then it's included in our probability. This also includes any outcomes that would fall under both events at the same time, and that's where we have to consider adjusting our probability formula. So the probability of a union of one event or the other is going to be the probability of each event added together minus the probability that both occurred at the same time. Why do we have to deduct this number in this case? Well, think of these two events, rolling something that's odd and rolling something that's divisible by 3. Are those events mutually exclusive? In other words, if you roll an odd number, is it or is it not possible to roll something that's divisible by 3? If it's impossible to roll something that's both odd and divisible by 3, then we would say that these events are mutually exclusive. What we know, though, is that it is possible to roll something that is both odd and divisible by 3, which means that these events are not mutually exclusive. If they're not mutually exclusive, if there are some outcomes that represent both events occurring at the same time, then again, we have to keep in mind that those outcomes were counted as part of two different probabilities. Because they were double counted, we have to subtract that intersecting probability in order to balance out this sum and avoid double counting. So the probability of one event or the other is the sum of the individual probabilities minus that particular probability for whatever outcomes resulted from the intersection of our two events. So what's the probability of A? Well, A is defined as the event where we roll something that's odd. Well, how many ways are there to roll something that's odd? We could roll a 1, a 3, or a 5. So there's 3 ways to roll an odd out of the total 6 possibilities. Now I would leave that non-reduced, and I'll explain why in just a minute. The next event is rolling a number that's divisible by 3. In other words, something that 3 divides evenly into. Well, the numbers within a roll of a die that are divisible by 3 are going to be 3 and 6. 3 divides into 3 evenly, and 3 divides into 6 evenly. So there's 2 different ways to roll a number that's divisible by 3 out of our 6 total possibilities. So 2 out of 6 is going to be the probability for B. But again, we have to subtract the probability of the intersection. Which event was double counted here? Well, the particular outcome that was double counted is the outcome of getting a 3. 1, 3, and 5 for odds, and then 3 and 6 for divisible by 3. So that 3 was double counted as part of both probabilities. So the probability of getting something that is both odd and divisible by 3, well, there's only one way to get something that falls under both of those categories. So the probability of the intersection is 1 out of 6, which is actually what we just calculated above. The reason it may be helpful to just leave those denominators as is and not reduce your fractions is because now you have a common denominator, and if you were to combine these fractions by hand, you can now just combine their numerators together. So 3 plus 2 is 5, minus 1 is going to give you 4 over that common denominator of 6. So our probability for A or B is going to be 4 out of 6, which reduces to 2/3 or approximately 0.667. Okay, let's look at another example. So suppose instead of rolling one die, now we're rolling two. So we talked about this sample space in the last video. We went through and defined that, and I have it listed here. So think of it as ordered pairs. Each element in the ordered pair is how many dots are on one of the dice that's rolled. First question, what is the probability that a sum of 7 or 11 turns up? So define our two separate events. So the first event is that we roll a sum of 7. The second event is that we roll a sum of 11. Now, are these two events mutually exclusive? In other words, if we roll a 7, if we roll a sum of 7, is it or is it not possible to also be rolling a sum of 11? Well, there's no way we can roll a sum that's both a 7 and an 11 at the same time. It just can't logically happen. So that means these two events are going to be mutually exclusive. If they're mutually exclusive, then all we have to do to find the probability of their union, of finding one event or the other, is to sum up the individual probabilities of the individual events. Because again, there's no overlap, so there's no risk of double counting outcomes in each of these probabilities. So let's look at the probability for a sum of 7. How many different ways are there to roll a 7? Well, we could roll 6-1 or 1-6, 5-2 or 2-5, and then 4-3 or 3-4. So there's 6 ways in total to roll a 7 out of the 36 total possibilities. So our probability is going to be 6 out of 36 to roll a sum of 7. Now what about a sum of 11? We could roll a 6 and a 5, or we could roll a 5 and a 6. So 2 outcomes out of the 36 in total. So 2 out of 36 is the probability of rolling an 11. Because of those common denominators, we can just add the numerators together. So it's going to be 8 out of 36 for the probability of our union. That's going to reduce to 2 out of 9, or approximately 0.222. Okay, what is the probability that both dice turn up the same, or that a sum less than 5 turns up? Okay, so a little bit more complicated in terms of how we've defined these events. So go back to just the individual events, look at one at a time. We do need to determine whether or not these events would be considered mutually exclusive, but we'll get to that in just a second. I want to think of what kind of outcomes represent these two different events, because again, these are slightly more complicated. So the probability that both dice turn up the same, so rolling the same number, would be defined as our first event. So sometimes that's called rolling doubles. What's the probability that we roll doubles? That's event A. Now event B is rolling something less than 5, which means we could roll a 2, we could roll a 3, or we could roll a 4. So any roll that adds up to less than 5 is considered part of B. So let's think about all the different outcomes representative of these events. So rolling the same thing, rolling doubles. How many different ways are there to do that? Well, we could roll 1-1, 2-2, 3-3, 4-4, 5-5, or 6-6. Those are the only outcomes representative of rolling the same outcome on each die. So that's a total of 6 different outcomes out of the 36 total possibilities. So the probability of A is going to be 6 out of 36. Now, because we're taking a union of two events, we're going to add up the probability of the second event, which is rolling something that's less than 5. So we could roll a 1 and a 1 for a 2, a 2-1 or a 1-2 for a 3, or 3-1, 2-2, and 1-3 for a 4. Notice it says strictly less than 5, so outcomes that result in exactly 5 are not included as part of the probability here. So 1 outcome, 2 more, and then 3 more for a total of 6 outcomes. So the probability of rolling something that's less than 5 is going to be 6 out of 36. Now that's not the whole story, because I want to go back to the actual outcomes we looked at for our two events. Remember, doubles were on the main diagonal from top left to bottom right, and then rolling something less than 5 was in that top little triangle. So notice if you look at the overlap, there are actually 2 different outcomes that represent rolling dice the same and also rolling dice that sum to less than 5. So the outcomes 1, 1 and 2, 2 were actually counted in both of these probabilities. What that means, because we have overlapping outcomes, is that these two events are not mutually exclusive. Because there is a set of outcomes that represents both happening at the same time, these two events are not mutually exclusive. So those two outcomes were counted as part of both of these probabilities. Because they were double counted, we now subtract that double count. We subtract the probability of both outcomes occurring at the same time. So there's two ways to get an outcome that represents dice rolling the same and dice also rolling so that they sum to be less than 5. So the probability of intersection is going to be 2 out of 36. So our total probability is going to be 6 plus 6 minus 2, which is 10 out of 36, which reduces to 5 out of 18, or approximately 0.278. So that's going to be our probability there. Okay, now let's look at cards. So a single card is drawn from a standard 52 card deck. Calculate the probability of each event. Okay, first event is a spade or a heart is drawn. So event 1 is drawing a spade. Event 2 is drawing a heart. So we'll call A spade and B heart. Are these events mutually exclusive? In other words, if we draw a spade, is it possible to also be drawing a heart at the same time? Well, we know based on how the suits are defined, a card is a spade or a card is a heart, but it can't be both at the same time. Spades are black cards, hearts are red cards. So there won't be any outcomes in the sample space representative of both of these events occurring at the same time. That means these two events are going to be mutually exclusive. So if we want the probability of one event or the other happening, we're just going to sum their individual probabilities. So what's the probability that we draw a spade? Well, out of the deck of 52 cards, we're drawing one card. How many ways are there to draw a spade? Well, there's 13 ways to draw a spade out of the 52 possible draws. So 13 out of 52 is the probability that we draw a spade. Well, what's the probability that we draw a heart? Well, there's 13 ways to draw a heart out of the 52 cards in the deck. So that probability is going to be 13 out of 52. So we're going to sum their probabilities because we're taking the probability of the union. So that's going to come out to 26 over 52, which is 1/2. So half of the time you will draw a spade or a heart. Well, what about the other half of the time? What would you draw? Well, the only other possibilities would be clubs and diamonds. So the other half of the time you would draw either a club or a diamond. Okay, what about the probability that a king or a queen is drawn? So event A is drawing a king, event B is drawing a queen. Are these events mutually exclusive? If you draw a king, can you also be drawing a queen at the same time? Again, the answer is no. If a card is a king, then that card can't also be a queen at the same time. So if you're only drawing one card, it's either going to be a king or it's going to be a queen. So that means the probability of the union, the probability of drawing a king or a queen, is going to be the sum of the probabilities for each of the events. Well, how many ways are there to draw a king? There's 4 kings in the deck, one for each suit. So there's 4 kings to draw from out of the 52 cards in the deck. So the probability of drawing a king is going to be 4 out of 52. Notice that the probability for drawing a queen is the same because there's the same number of queens in the deck, so also 4 out of 52. Keep in mind, as we're defining these probabilities, we're not actually drawing a card from the deck. We're just analyzing the deck of 52 cards theoretically. So don't think of it as you draw a king and now you have one less card to draw from, and so you're drawing out of 4 queens, something like that. There's a little bit more involved to that, or maybe you can think of it as being simpler than that. You don't have to worry about whether you draw and then return something to the deck. We're just looking at things from a theoretical standpoint. So the probability of the union is going to be the sum of those two probabilities, which comes out to 8 out of 52, which reduces to 2 out of 13, or approximately 0.154. Okay, let's look at one more combination. So what's the probability that an ace or a diamond is drawn? So event A is going to be drawing an ace. Event B is going to be drawing a diamond. Now, are these events mutually exclusive? In other words, if you draw an ace, is it possible to also draw a diamond? Well, in this case, the answer is yes, it is possible to draw something that falls under both of these events. What would it be? Well, if it's both an ace and a diamond, well, then it has to be the ace of diamonds. That's going to be the only card, though, that represents both of these events occurring at the same time. But because that card will be counted as part of the outcomes for aces and the part of the outcomes for diamonds, we do have to make sure that that outcome is not double counted when we calculate our probability. So the probability of event A or event B is going to be the sum of the probabilities. So probability of the ace, there's 4 aces in the deck out of 52. Probability of drawing a diamond, well, there's 13 diamonds out of the deck of 52. And then we double counted the ace of diamonds in both of these probabilities. So we have to subtract that probability. There's one outcome that represents both of these occurring at the same time. So that's going to be 1 out of 52. So we're going to subtract that probability so that our probability isn't too high. So 4 plus 13 minus 1 comes out to 16 out of 52, which reduces to 4 out of 13, or approximately 0.308. So that's going to be the probability that we draw an ace or a diamond. Okay, one more. What about a club or a face card? So a club is a suit, and then face card means either a king, a queen, or a jack. Aces are not considered to be face cards. So event A is drawing a club, and then event B is drawing a face card. Are these events mutually exclusive? Can you draw something that's a club and a face card at the same time? Well, again, the answer is yes. Say you were to draw the king, queen, or jack of clubs. Each of those 3 cards is an outcome that falls under both of those events. So those 3 cards as outcomes are counted twice when we calculate the individual probabilities. So we have to subtract that intersecting probability in order to make sure we don't double count. So the probability of A union B is going to be the probability of A. So how many ways are there to draw a club? Well, there's 13 clubs in the deck out of the 52 cards in the deck, so 13 out of 52. What about a face card? Well, there's 12 face cards in the deck. How do we know that? Well, face cards are going to be kings, queens, and jacks. So there's king, a queen, and a jack for each of the 4 suits. So 3 different face cards for 4 suits. That's a total of 12 in the deck. So 12 ways to draw a face card out of the 52 cards in the deck. But what did that double count? That double counted the king of clubs, the queen of clubs, and then the jack of clubs. Each of those 3 cards was counted as a part of both of these events. So there's 3 ways to get an outcome that overlaps these 2 events. So 3 out of 52 is the probability we have to subtract. So 13 plus 12 minus 3 is going to be 22. So 22 out of 52, which reduces to 11 out of 26, or approximately 0.423. So those are a few examples of calculating probabilities of unions, and then using the probability of the intersection to look at those slightly more complicated cases when we don't have events that are mutually exclusive. Now, the complement of an event is going to be the set of all events in our sample space that are not in our particular event. So it's all the other outcomes other than the ones represented in an event. So if we were going to use set notation, the notation for the complement is the prime notation. So if A is an event, A prime represents the complement. A prime is defined as all of the outcomes in the sample space such that they are not outcomes in the event. So it's everything in the sample space other than what's in the event that we started with. So for instance, when I mentioned spades or hearts, those were the 2 particular combinations that we were looking at in terms of our events. The complement of drawing a spade or a heart is drawing the other cards in the deck, which would be clubs and diamonds. So if we were to think of our event as drawing a spade or a heart, the complement of that event would be drawing a club or a diamond. It's all the other possible outcomes that are not represented by the event in question. Now, if we have an event and we have its complement, we also have ways to use probability to calculate one probability versus the other. So the probability of an event's complement is going to be 1 minus the probability of the actual event itself. We can also rearrange this formula, so the probability of an event, say we were to solve for that. So imagine adding this to both sides and then subtracting the probability of the complement. In that case, the probability of the event itself is also 1 minus the probability of the complement. So they work both ways. We can also use both formulas in different ways. So in some cases, it's actually easier to calculate a complement than it is to calculate the probability of an event itself. So sometimes, just depending on how an event is defined, it may be easier to use the complement and work backwards. We'll talk about that in just a minute. So let's look at an example. A single card is drawn from a standard 52 card deck. Calculate the probability that you do not draw a number card. Okay, so the event is going to be the event that doesn't use the word not. The word not is the red flag word that means we're looking at a complement. So the event is drawing a number card. We're looking at the complement of that event. So the event is drawing a number card, which would be cards 2 through 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we're interested in the probability of not drawing a number card. In other words, a complement. So the formula for this probability is going to be 1 minus the probability of the original event, which is drawing a number card. Well, how many ways are there to draw a number card? We can draw 2 through 10, and then we have 4 different suits. So count it, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 9 cards, okay? So that's 9 cards per suit. There's 9 cards that are hearts, 9 cards that are diamonds, 9 that are clubs, 9 that are spades. So that's going to be a total of 36 cards out of the deck that are number cards. So the probability of drawing a number card, there's 36 ways to draw a number card out of the 52 possibilities. Now this particular subtraction, you can just do in your calculator if you want. Technically speaking, you have to have a common denominator to add or subtract fractions. How would you do this by hand? Well, if you were to take 1 and rewrite 1 as a number with a denominator of 52, what would that look like? Well, 1 could be written as 52 over 52. So 52 over 52 minus 36 over 52 would then give you the fraction you need. If you do this in the calculator, either you have a calculator that will give you the reduced fraction, or you have a calculator that'll give you the decimal. Now, if you have a graphing calculator, you can probably type this in, but it's going to give you a decimal. Now, be careful when you type this in. Keep in mind what this actually represents. If you just type 1 minus 36 over 52, or 1 minus 36 over 52, just no parentheses, anything at all, your calculator may not calculate exactly what you want. So it's just to be safe, you may want to put parentheses around the actual fraction and then do 1 minus that, the fraction in parentheses, just so it's very clear what you're considering to be going together in your actual algebraic expression. But once you get this, if it gives you a decimal, remember you can convert it to a fraction and that'll give you the reduced form of the fraction. So the probability that you do not draw a number card is 1 minus the probability that you do, which comes out to 4 out of 13, or approximately 0.3008. Now I thought the next example was kind of interesting. The circle graph below shows the time breakdown in minutes for various aspects of an average 190-minute NFL television broadcast. What is the probability that a minute of the broadcast is not devoted to gameplay or actual football? Okay. Well, we're looking again at a complementary event because of that word not. So we're going to define the event as the version of this that doesn't use the word not. So if we were to change the question to what is the probability that a minute of the broadcast is devoted to gameplay, that tells us what the event is, and then we're looking for the probability of the complement. So the event is that from the broadcast we pick a particular minute that's devoted to gameplay out of all the different ways the broadcast is divided up. So we're interested in the complement of this event, choosing a minute that's not devoted to gameplay. So the probability of the complement is going to be 1 minus the probability of the event. Okay, so again, the event is you pick a minute that's devoted to gameplay. What sort of other things happen? Well, remember there's commercials, and then there's a lot of just standing around, honestly. They have tons of shots of just people standing around, shots of the crowds, things like this. This particular pie chart has broken it down for you based on this particular data. So notice the only wedge representative of actual gameplay that's being broadcast represents 11 minutes out of 190. So actual gameplay is 11, so there's 11 ways to get a minute of gameplay out of the 190 minutes representative of the entire broadcast. So the probability of the event A is going to be 11 out of 190. And again, you can do this subtraction in your calculator. 1 minus 11 out of 190 comes out to 179 out of 190, or approximately 0.942. So what does this mean? Well, it means if you were to just say record the broadcast and then randomly fast forward to 1 minute, almost 95% of the time, you're going to fast forward to a minute that's not actual football, just shots of people standing around. Maybe you fast forward to a commercial, something like that. That's what that means. The other fraction of the time, which in this case would be roughly 5% of the time, represents actual football, actual players playing, running a play. Okay. Now again, sometimes it's easier to calculate the probability that an event doesn't happen and then use it to calculate the probability that an event does happen. So anytime we have an event versus its complement, they always work formulaically in the same way in terms of probability. 1 minus the probability of one gives us the probability of the other. But sometimes just based on how an event is defined, if the event is defined in a complicated way, it may actually be easier to calculate the probability of the complement. If we know the probability of the complementary event, then we can use a version of the complementary formula to calculate the probability of our actual event. So let's look at a couple questions where we might use complements kind of working backwards. So for example, what is the probability of getting at least one heart in a 5-card hand dealt from a standard 52-card deck? Okay, now why would this not be a good problem to just approach from just the straightforward, calculate the number of ways to get the outcome, just do it like a normal probability problem? Why might this one be more difficult to do? The reason this particular event's probability is difficult to calculate is because of the term at least one heart. Well, what does that mean? Well, it means we'd have to consider one heart out of the 5 cards. We'd have to consider 2 hearts out of the 5 cards and then 3 other cards. We'd have to consider 3 hearts out of the 5, 4 hearts out of the 5, and then we'd also have to consider the possibility that we get all 5 hearts when we draw. So what that means is because of this term at least in front of that, in front of the choice of 1 heart, it actually puts us in a situation where there are a lot more outcomes than if it were just saying, what's the probability of getting 1 heart in a 5-card hand, exactly 1 heart. That term at least, or if we were to change it to at most, something like that, it means we have to actually break it down ourselves and think about all the different possibilities for ways that we could get at least 1. And in this case, that's actually pretty multifaceted. There are a bunch of different ways to get at least 1 heart, and we would have to actually come up with ourselves and calculate ourselves all the different ways we could get at least 1 heart. It's not as straightforward as doing a single combination like we've been able to do before. So here's how we're going to approach this. We always need to start by defining the experiment and the sample space. So our experiment is dealing 5 cards. So the sample space is all the 5 card hands. We actually calculated this value before. So out of the 52 cards, we're taking a combination of 5, and that represents the size of the sample space. That's all the different 5 card hands we can get. So 52 combination 5 comes out to 2,598,960. So we know automatically that's going to be the denominator for our probability. The denominator is always the size of the sample space for the experiment. What becomes more complicated is the numerator. How do we determine what the numerator is? Well, let's define our event, and then we're actually going to use the complement here. So the event is getting at least 1 heart in our 5 cards. But remember, that can look a bunch of different ways. That could be 1 heart and then 4 others. It could be 2 heart and 3 others, 3 hearts and 4 other, or excuse me, I'm getting crazy. Sounds kind of crazy here. 1 heart and 4 others. Let's try that. 2 and 3. We could do 3 and 2, 4 and 1, or all 5 hearts. The problem with actually approaching this probability directly is each of those individual combinations representative of the event, we would have to calculate probabilities for individually, which would be tedious. More than likely that would be pretty tedious. Instead, we're going to use the complement of this event, and we're going to work backwards. So if the event in question is drawing at least 1 heart, the complementary event is not drawing at least 1 heart. If you were to put the word not in front of this, not at least 1 heart, well, that doesn't sound very grammatically correct, but what does it actually mean? Well, the opposite of drawing at least 1 heart is drawing no hearts, none at all. So you draw all 5 cards and none of them are hearts. This is the complementary event to the event in question that we're trying to determine the probability for. So the complement is going to be no hearts at all in all the 5 cards. Well, that we can determine more directly because we don't have to break it down into individual specific combinations. We're just looking at all the possibilities where we draw from the deck where there are no hearts. Well, how many ways are there to get a hand of cards where there are no hearts? Well, how many cards in the deck are there that aren't hearts? Well, we start with 52 cards. If we were to take out all the hearts in the deck, how many do we have left? There's 13 hearts. Imagine taking all of those out. If we take all of those out, there's 39 cards in the deck that are left. So the number of ways to get no hearts is going to be 39. We're choosing from the 39, and then we're choosing the 5. But again, we're choosing specifically from the 39, choosing from all the cards other than the hearts. So 39 combination 5 is going to come out to 575,757. That's going to be all the different hands we could get where there are no hearts. We took all the hearts out of the deck and we just dealt from the remaining cards. Well, we want the probability of getting at least 1 heart, but we can find the probability of the complement. So the probability of getting no hearts is going to be this particular value divided by this particular value. How does that help us if this is not the event we're interested in? Well, we use the complement formula backwards. So we want this particular probability. It's going to be defined as 1 minus the probability of the complementary event, which in this case is drawing no hearts. We know what that probability is based on the counts we just did. So the probability that we get at least 1 heart in our 5-card hand, in other words, again, 1 heart and then 4 others, 2 hearts and 3 others, so on and so forth, all those different possibilities, rather than calculating it directly, it's also defined as 1 minus the probability of our complement, which is going to be the fraction based on these 2 counts. So that's going to come out to reduced. Again, if you put this in your calculator, you can convert it to a decimal and then convert it back to a fraction and it will reduce it. It's going to come out to 7,411 divided by 9520. That's going to be our probability, or approximately 0.778. Okay, let's look at another problem where we might need to work backwards. So we're looking at an event. The event may be difficult to calculate the probability for, but the complement defines a simple event and we can actually determine the probability of the complement and work backwards. Okay, so a shipment of 45 parts, including 9 that are defective, is sent to an assembly plant. The quality control division randomly selects 10 parts for testing and rejects the entire shipment if 1 or more in the sample are found to be defective. Okay, I want you to pay attention to that terminology, 1 or more. What is the probability that the shipment will be rejected? Okay, so let's go through and break this down. So 45 parts are being shipped. We happen to know that 9 of them are defective. Okay, so when the group gets this particular delivery, they want to determine whether or not they're going to keep the shipment, and so they're going to test a sample, and based on what their test results in, that's going to determine whether or not they're going to keep it or whether they're going to return it. So 9 out of the 45 we know to be defective. They're just going to randomly pick 10 out of the 45 and test them. If they find even 1 that's defective, then they'll send it back. If they find more than 1, they're going to send it back as well, but they have to find at least 1, and that will determine if they're going to send it back. We want to know what's the probability that it is sent back. Another way of translating that is what's the probability that they test the 10 parts and they do find 1 or more that are defective in the sample. So there's 9 that are defective. All they would have to do is, out of that group of 10, end up drawing 1 of those potential 9. Okay, so that's in general what's happening in terms of the situation. Again, take a minute, pause the video if you need, read through this again, think about the actual situation. Making sure you have your head wrapped around this situation is going to be important, because now we have to define the sample space, we have to define our events. Okay, so what is the sample space? What's the physical action that we're doing? Well, the control division is picking and testing a sample. That's the physical action being taken. So they're selecting 10 out of the 45. So our sample space is all the different possible selections of 10 parts. How many different ways can you choose a sample of 10 out of the 45? That represents the count for our sample space. Well, we have 45 to choose from, and we're choosing 10. Why is this a combination? Well, it doesn't matter what order we choose them in. We're still going to test them all. It doesn't say we're worried about what order we test them in. We're just choosing 10 out of the 45 to test. So the count for our sample space is going to be 45 combination 10. Really big number. That's billions. So 187,286. That's kind of mind-blowingly large. And again, there's no way you could actually make a list of all the different combinations, but believe it or not, it actually comes out to a number this big. So that we automatically know is going to be a probability denominator. The count for the sample space is the denominator for the probability. Well, what is the event we're interested in? The event we're interested in is the shipment is rejected. Okay. Well, why would the shipment be rejected? It would be rejected if we test the 10 and 1 or more is defective out of the sample. So we test our selection of 10 and 1 or more is found to be defective. Now, why can we not just directly calculate the probability? Well, we'd have to count all the different ways to find 1 or more that's defective. Well, kind of like with at least 1 heart, this is a very similar situation. So remember, that could be 1 heart and 4 others, 2 hearts and 3 others, 3 hearts and 2 others. In other words, there's a bunch of different ways we could end up with something that represents a hand of cards with at least 1 heart. And we have to look at all those different situations individually. Well, the same kind of thing is happening here. If 1 or more are defective, then we send it back. So what's the probability that 1's defective? We'd send it back. What's the probability that 2 are defective? We'd send it back. How about 3? We'd send it back. All the way up to the possibility of choosing 9 in total, since there are 9 defective ones, all the way up to that possibility. If we picked 10 and 9 of them were defective, again, we'd send it back. So we'd have to enumerate each of those different situations, each of the different possible numbers that we could find to be defective. we'd have to find the probability in each of those situations because each of those has a different count in terms of the number of outcomes representative of that particular combination. So calculating the probability for this event directly is pretty complicated because there's so many different ways we can actually achieve this event. But let's think about what the complement of this event is. The event is one or more are found defective. Well, what's the opposite of not one or more is defective? What's the opposite if we put the word not in front of that? Well, if one or more or not defective, then the opposite of that is that none are defective. We don't find any that are defective. Well, that is straightforward to calculate because that only represents one possible combination of values. It's you choose your sample, you test the whole sample, and the whole sample is clean. Okay, now here's where it gets a little bit more complicated. We have to think about how we would specifically choose a sample that's clean, where nothing is defective. In other words, what is the count? How many outcomes are involved in this complementary event where none are defective? Well, think about the situation. We have a box of 45 things and 9 are defective. We want to determine how likely are we not to choose anything that's defective out of those 45 where 9 are actually defective. Well, what's the only way you could choose your sample so that none of them are defective? Well, the only way you could do that is if you're only drawing from the non-defective parts. Well, how many of those are there? Well, if there's 45 parts in total and 9 are defective, then we know that 45 minus 9, in other words 36, the other 36 parts in the shipment of 45 are the ones that are not defective. So the only way to choose a sample where none are defective is to choose from the other 36 in the shipment. So the number of elements in the complementary event are going to be 36, so we're choosing from the 36 non-defective parts, 36 combination, and then we're choosing a combination of 10 because we're selecting 10 parts to sample. Okay, so 36 combination 10 comes out to 254,186,856. This is the total number of ways to choose a sample where none would be defective. We're choosing the sample of 10 because that's the experiment, but we're choosing a sample where none are defective, so we're choosing from the 36 parts that are not defective. Okay. Well, remember, this is not the event we're interested in. The question is, what is the probability that the shipment will be rejected? In other words, what is the probability that we pick a sample where one or more parts are defective? Well, we decided we can't really calculate that directly just because that can look a bunch of different ways. But we can calculate the probability of the complement, and then we subtract 1 minus that probability, and that's going to give us the probability of that more complicated event that we can't calculate directly. So the probability that we return the shipment, in other words, one or more, 1, 2, 3, 4, all the way potentially up to 9, all those different combinations that result in us returning the shipment, that's going to be 1 minus the probability of the opposite outcome, which would be that none are found to be defective. So 1 minus that probability. Well, that probability, there's this many ways to pick a sample of 10 where none are defective. That's the number of ways, since we're choosing out of the 36 that are not defective, out of the total number of ways to choose the 10 parts to test with no restrictions, choosing from the whole selection of 45. That's kind of a crazy looking fraction, but again, just pay attention to the fact that the numerator is smaller than the denominator. That's the important part. So the fact that the numerator is smaller than the denominator, even though these are big numbers, this whole fraction is still something that's less than 1, just based on how the numerator and denominator are related. So 1 minus this number would be a really strange looking fraction, but the approximate decimal version for that is going to be 0.920. So about 92% of the time, we would fall under this event if we were randomly choosing one of the outcomes from this particular sample space where we're choosing selections of 10 parts. About 92% of the time, one or more parts is found to be defective, and then we're going to return the shipment. So how do you know when to calculate a probability directly versus this case when the probability needs to be calculated using that complement and working backwards? Pay attention to those terms at least, or at most, at minimum, something like that. In those situations, usually that means you have to enumerate more than just individual counts. You have to enumerate possibilities, and then you have to count for each possibility. In terms of the cards, at least one heart. You have to think about all the different ways that could look. That could look like one heart and then four others, two hearts and then three others, so on and so forth. Because each of those combinations results in a different count. You'd have to do the count for each of the different combinations that fits under this event. And then you'd have to calculate probabilities individual for each of those counts. Same kind of thing here. Returning the shipment results when one or more is defective. So one or more being defective could mean that one is defective, or two, or three, or four, all the way up to 9. So if you wanted to calculate the probability of this event directly, you would have to calculate how many ways there are to have exactly one that's defective. In other words, one is defective and the other 9 are not. You'd have to calculate the number of ways that 2 could be defective. In other words, 2 out of the sample of 10 are defective, the other 8 are not. So on and so forth. You'd have to calculate all the different possibilities and then find the probability based on all of those separate counts. It is doable, it's certainly doable, but the logistics of doing it are pretty complicated, and it's pretty easy to make a mistake if maybe one of your counts is off. That kind of trickles down through the rest of the problem. So if the complementary event is simpler, then we can use the complementary event, we can work backwards, and we can find the probability for the actual event in question. Okay, let's finish up with a discussion of odds. So odds are going to relate closely to this idea of the complement of an event. So in many real-world contexts where probability is known, it's often customary to describe the odds that are either for an event happening or against an event happening. We have several different notations for this. We're going to use fractional notation for odds, but sometimes you'll see odds expressed with a colon, so one value compared to another value. Sometimes you'll just see the word to, so one value to another value. All of these are considered correct for odds, but just because we want to be able to work with these algebraically, we're going to use fractions, which are going to be easiest to work with. So when we define odds, we need to know two things. Number one, we need to be able to know the probability of an event, but we also have to know the probability of that event's complement. So either we know them both or we can calculate them both. And again, keep in mind, if you know the probability of an event, the probability of the complement is just always going to be 1 minus that number. So having one probability means the other one is pretty straightforward to calculate. So the odds in favor of an event happening are represented by the probability that the event does happen divided by the probability that the event does not happen. The odds against an event, that's going to be the probability that the event does not happen divided by the probability that the event does happen. Notice these two values are going to be reciprocals of one another. So this fraction, if you were to flip it upside down, gives you the opposite odds. So suppose you're asked for odds for and odds against. All you have to do is calculate one, and then you take the reciprocal, and automatically you have the odds in, against, or in favor, depending on what you started with. So let's look at a couple examples. What are the odds for rolling a sum of 7 in a single roll of 2 fair dice? And then what are the odds against rolling a sum of 7? Well, we have to start with the probabilities. What's the event in question? The event in question is rolling a sum of 7. Well, we looked at this probability before. We have to think about, in our sample space, representative of rolling 2 dice, how many ways are there to roll a 7? Well, remember, you could roll a 1 and a 6 and a 1, 2 and a 5, 5 and 2, 3 and 4, and then 4 and 3. Those are all the different ways to roll a 7. So 6 different ways to roll a 7 out of 36 possible outcomes, 36 different combinations for how you can get a distinct roll for your 2 dice. So the probability of rolling a 7 is going to be 6 out of 36. Now we also need the probability of the complement. Here's a shortcut. See that denominator of 36? If the numerator is 6, think about how much more you'd need to get from 6 to 36. Think about the difference between the two. The difference in this case would be 30. Well, that automatically means that the fractional version of the probability of the complement is going to be 30 out of 36. If 6 outcomes represent the event, then the other outcomes in the sample space represent the complement. So if 6 out of 36 represent the event, then the other 30 out of the 36 represent the complement of the event. So the odds for this event, the odds in favor of the event, it's the probability the event does happen divided by the probability that it doesn't happen. Now this is technically a complex fraction. It's fractions inside of a fraction. There is a shortcut for simplifying this though, so don't be overwhelmed when you see this. Here's the shortcut. Notice those matching denominators of 36. Because those are matching components in the big numerator and the big denominator, they actually cancel out. So those matching denominators of 36 actually just go away. And we're just left with 6 in the numerator and 30 in the denominator. Kind of a shortcut. Now that's only going to work if you don't reduce your probabilities to start with. They have to have the same denominator so that that matching denominator cancels. But in this case it does. That goes to 6 out of 30, which reduces to 1 out of 5. Now when we're talking about odds, we're going to leave it in fractional form. You're not going to convert that to a decimal. You're going to leave that as is. So the odds in favor of rolling a 7 are going to be 1 to 5, 1 out of 5. Now once you have this, the odds against are quick to calculate. So 1 out of 5, you just take its reciprocal. So if the odds for the event are 1 out of 5, the odds against are going to be 5 to 1. Now this should probably make you feel a little uncomfortable because you see something like this and you know algebraically I'm not supposed to leave it like this. I should reduce that to a 5. When we're talking about odds, we're talking about a comparison of two values. So even though algebraically speaking, normally this means we're looking at a whole number, 5 divided by 1, we're looking at the number 5. When we're talking about odds, we're still going to leave it as 5 over 1 so that we have the comparison of one value to another. Now what do the odds really mean? What they mean is how many times you will have the event happen versus how many times you won't. So the odds for our event, think of that as every one time that the event does occur, there will be 5 times that the event doesn't. Or if you think of the odds against, every 5 times the event doesn't occur, there will probably be 1 time that it does, just from a probability standpoint. So that's just a basic calculation of odds, and that's sort of how you interpret it from there. Now let's look at another example. So in a lottery game, a single ball is drawn at random from a container that contains 25 identical balls numbered 1 through 25. Find the probability and the odds that a number drawn is something like the following. So possibility number 1, find the probability and the odds that a number drawn is even or a multiple of 7. Okay. So notice this is a union of 2 events. Even is one event, multiple of 7 is another event. So even we're going to define as event A, and multiple of 7 we're going to define as event B. We want to know what's the probability that we get this particular compound event, and then what are the odds in favor of getting this event. Okay. So we know when we're taking the probability of a union, we're going to sum the individual probabilities, and then if there's any overlap between those 2 events, we're going to subtract the overlap. Okay, so the probability that we get something that is even. Well, we have numbers from 1 to 25. The even numbers are going to be 2, 4, 6, all the way up to 24. Count it, that's going to be 12 of them. So 12 out of the 25 numbers are going to be even. So the probability of getting something that's even is going to be 12 out of 25. Now, what about getting a multiple of 7? Well, if we're going to 1 and stopping at 25, the multiples of 7 are going to be 7, 14, and 21. So there's 3 different ways out of the 25 to get a multiple of 7. Now, are these events mutually exclusive? Is it possible to get a number that's both even and a multiple of 7 in this particular group of numbers from 1 to 25? Well, the one number that falls under these 2 scenarios is the number 14. 14 is an even number, and it's a multiple of 7. Keep in mind, again, the multiples of 7 are far fewer than the even numbers. The multiples of 7 are 7, 14, and 21. 14 is the only number in this event that's also an even number. So there's one outcome that was double counted in these probabilities. So one outcome out of 25 was double counted, so we subtract that probability. That means the probability of our union comes out to 14 out of 25, or 0.56. So what about the odds? We also want to know the odds in favor of this event happening. That's going to be the probability that our event does happen divided by the probability that it doesn't happen. Well, if 14 out of the 25 total outcomes represent this event, the other outcomes in the sample space represent the complement. So 14 out of 25 represent our event. That means the other 11 do not fall into event and therefore fall into its complement. So the probability of the complement is going to be 11 out of 25. So 14 out of 25 divided by 11 out of 25. Notice again, we've got that common denominator. That can be canceled. And so our odds are going to be 14 to 11 in favor of this event happening. Okay, let's look at another. What about getting a number that's prime? In other words, the only things that divide into it are going to be 1 and itself, and greater than 20. Okay, well, if you need to look up prime numbers, look those up. In general, 1 is not considered to be a prime number. 2 is the first prime number, and 2 is also the only prime number that's an even number. So our prime numbers from 1 to 25, think about all the numbers that you can't divide anything else into. We've got 2, 3, 5, 7, 11, 13. Let's see, the next one would be 17, and then 19, and then 23. Okay. All the other numbers not listed, we can divide something other than 1 and themselves into them. So there are going to be 9 prime numbers. Okay. Now, don't forget, again, 1 is not considered to be a prime number. So when you first introduce the concept of prime numbers, you may call 1 a prime number. 1 is not actually defined as a prime number. 2 is going to be the smallest prime number. So we start counting at 2, and then our largest one is 23. So 9 out of this group of 25 numbers are prime numbers. So the probability of choosing a prime is going to be 9 out of 25. Now, what's the probability of choosing something that's greater than 20? Well, that could be 21, 22, 23, 24, or 25. So there's 5 different ways out of 25 to get a number that's greater than 20. Now, are these events mutually exclusive? Is it possible to get a number that's both prime and greater than 20 at the same time? Well, remember that number 23 was a prime number. So 23 is both prime and it's greater than 20. So that one outcome is double counted in these 2 probabilities. So we subtract 1 out of 25, and that's going to give us 13 out of 25 as our probability for the union. Okay, so the odds in favor of our event getting a prime or getting a number that's greater than 20, it's going to be the probability that we do get that combination, so 13 out of 25. Well, if 13 out of the 25 outcomes represent this event, then the other 12 out of 25 represent the complementary event. So getting something that's not prime, getting something that's not greater than 20. So 13 out of 25 over 12 out of 25, we can reduce that common denominator. So we have 13 to 12 as our odds. Okay, let's look at one more example, and then we will move on and we'll look at this in a different context. What about a multiple of 2 or a multiple of 5? Okay, so event A is getting a multiple of 2. Event B is getting a multiple of 5. Well, how many ways are there to get a multiple 2? Translate that as even numbers. We actually just looked at even numbers a moment ago. We can get a 2, a 4, a 6, all the way up to a 24. So 12 numbers in that group out of the 25 are multiples of 2. Now, what about multiples of 5? Well, if we're going from 1 to 25, we have 5, 10, 15, 20, and 25. So 5 out of 25 numbers are going to be multiples of 5. Are these events mutually exclusive? Are there any numbers that are multiples of 2 and also multiples of 5 within our group from 1 to 25? Well, let's start with the multiples of 5. It's probably going to be easier to start there. We had 5, 15, 10, or 5, 10, 15, sorry. 5, 10, 15, 20, and then 25. Okay. 10 and 20 are multiples of 5 that are also even. They're also multiples of 2. So those two outcomes, those were double counted. So we're going to subtract the 2 out of 25 that were double counted, which is going to give us 15 out of 25, which reduces to 3 out of 5. Okay, now you can leave it as 15 out of 25, or you can reduce it. For sake of the probability, we do want to reduce it. But if you want to think in terms of odds, you might leave it non-reduced. You technically don't have to, though. So if the probability of the union is going to be 3 out of 5, then the odds in favor of the event are going to be the probability that the event does occur, 3 out of 5. Well, if every 3 out of 5 times the event does occur, then the remaining 2 out of 5 times the event does not occur. So 3 out of 5 divided by 2 out of 5, reduce that common denominator, and that's going to give us odds of 3 to 2. Okay, so that's just a few examples looking at odds, again with slightly more complicated context using what we now know about finding the probability of a union. Now let's take some of this and let's apply this to empirical probability. So remember, empirical probability is based on actual data. All the situations we've looked at up to now, we've been looking at from a theoretical standpoint. We didn't actually run an experiment, we just analyzed the possible outcomes of an experiment and the fact that any one outcome is just as likely as any other. Empirical probability, we're basing our probabilities and our outcomes on specific data from specifically running an experiment and then tabulating our results. So from a result of 1,000 people in a small city, it was found that 500 people had tried a certain brand of diet soda, 600 had tried a certain brand of regular soda, and 200 had tried both types. If a person from this city is selected at random, what's the empirical probability that we get any particular combination as described? So I would start by organizing this in some type of meaningful format. A Venn diagram is a pretty good idea because the Venn diagram is going to allow you to determine specifically where categories overlap and then where things don't fit into a category. So how do we draw a Venn diagram for this situation? Well, what are we looking at? Our sets are people who've had a particular diet soda and people who've had a particular regular soda. So we might define our sets as D and R, D for diet and R for regular. Okay, so based on the Venn diagram, we can determine what overlaps, what doesn't, and then who falls under neither of these categories. Now we know there's 1,000 people in question, so our total for our different regions within the diagram should add up to 1,000. Now when we're labeling, we're always going to start in the center, in the overlap. What does that represent? Well, that's people who tried the diet soda and tried the regular soda. According to the description, 200 had tried both. So 200 people will fall into this overlap. We have to know that in order to determine how to label the other parts of the circles. So what do the other parts represent? Well, this part of the D circle is people that tried the diet soda but didn't try the regular soda. And then people, this part of the R circle, tried the regular soda but didn't try the diet soda. Well, it says 500, and you have to infer in total. 500 people in total had tried the diet soda. So that means the diet circle should have 500 people in total. Well, 200 were already accounted for, so that means the other 300 were ones that only tried the diet soda but didn't try both. Now it says 600 tried the regular soda, so 600 in total. 200 were already accounted for, so the other 400 had only tried the regular soda. Now we can't forget people who fall into the universal set, otherwise in this case known as the sample space. See, connection. 1,000 people in total fit into this diagram, but who's been accounted for? Well, 300 and then 200 and then 400 more people. That's only 900 people. So we only have 900 people that were then categorized further based on what they tried, but 1,000 people were surveyed. So what that means is that the remaining 100 people must have answered no to both questions. No, they hadn't tried soda 1. No, they hadn't tried soda 2. So there's also 100 people that are in the universal set that weren't further categorized into one of these circles. So once we have this diagram in place, this is going to allow us to determine our empirical probabilities. So the first probability is that our person in question has tried the diet soda or the regular soda, and then we want to determine the odds for and against this particular event. So the key word here is or, diet or regular, in other words, diet union regular. So we're looking for the probability that they tried the diet soda, the probability that they tried the regular soda. We'd add them together, and then we have to worry about that issue of mutual exclusivity. So what's the probability that someone tried the diet soda? Well, in total, 500 people tried the diet soda. So 500 out of 1,000 is the probability that someone tried the diet soda. What about the regular soda? Well, 600 people in total tried the regular soda. So 600 out of 1,000 for our probability. Now, are these categories mutually exclusive? If someone's tried the diet soda, is it possible that they also tried the regular soda? The answer is yes. And we happen to know that 200 people fall under this category. So those 200 people were counted in both of these probabilities. So we have to subtract that double counted probability so that it's only counted one time. So we're going to subtract 200 out of the 1,000. And that's going to give us a total of 900 out of 1,000, which reduces to 9 out of 10. Now we also want the odds. So the odds for this event and the odds against this event. So the odds for the event, in other words, the odds in favor that we choose someone who's tried one soda or the other and possibly both, well, the probability that they have is going to be 9 out of 10. And then the probability that they haven't, well, if 9 out of 10 have, then 1 out of 10 haven't. So 9 out of 10 over 1 out of 10, reduce that common denominator, and that means the odds are going to be 9 to 1. Now, once we have the odds for the event, remember odds for and odds against are going to be reciprocals. So if the odds for are 9 out of 1, then the odds against are going to be 1 out of 9. Okay, let's look at one more, and then we will be finished with this section. So what's the probability that a person has tried one of the sodas but not both? And then what are the odds for and against this event? Okay, one of the sodas but not both. In other words, just the diet soda or just the regular soda. Well, this is where that Venn diagram is going to be helpful. So just the diet soda, just that one, or just the regular soda, just that one. Well, how many people have just tried the diet soda? Well, we know 500 people in total tried it, but 200 tried both, which means that 300 people out of the 1,000 just tried the diet soda. So the probability of choosing someone that just tried that diet soda is going to be 300 out of 1,000. Now we also have to consider the probability that someone tried only the regular soda. So 600 people in total tried it, but 200 had tried both. So 600 minus 200 is going to give us the 400 that only tried the regular soda. So the probability of choosing someone that only tried that one is going to be 400 out of 1,000 for a total of 700 out of 1,000. Now, why do we not have to subtract anything here? Well, automatically, by definition, these two events are mutually exclusive. That phrase, but not both, means there is no overlap between these two categories. It means you fall under the category D, you fall under the category R, but not both. That both component is the component that we end up subtracting in order to deal with the issue of mutual exclusivity. So in this case, we don't have to worry about that based on how these two cases were defined. So our probability reduces to 7 out of 10. So the odds for this event, the odds in favor of choosing someone who's tried one but not both sodas, the probability that that happens is 7 out of 10. Well, if 7 out of 10 people fall under this category, then 3 out of 10 don't fall under this category, which reduces to 7 to 3. And then the odds against, again, that's just going to be the reciprocal, which is 3 out of 7. So this just takes our probability, extends it a little bit further. Sometimes we look at the probability of a single event. Sometimes we want to look at the probability of some combination of events. So now we know how to calculate the probability of one event or the other happening, and then also the probability of a complement. Once we know the probability of the complement, we can also calculate odds for and against an event.